Next one. Next one. Wait. Okay, good. You got it.
Thank you. Hi, so I'm Pedro. This is, not going to repeat, it's joint work with some people. I'm from TTIC. And so there has been a lot of work on trying to understand what kind of functions neural networks can represent. And along with that, we had many classic results. Most, if not all, of these results, they consider networks with a fixed or bounded number of units or parameters. So in other words, these results, they try to answer the question of, for some given function f, how large does a network has to be in terms of number of units or parameters to represent that function? The problem is these results, they don't really capture what we do in practice, especially in deep learning, where it's fairly common to have models whose number of parameters are 3 orders of magnitude larger than the data sets they trained on. I would even say that for this ResNext model, for example, is essentially infinite compared to the data set it's trained on, which consists of only 50,000 images. So perhaps the size of the network in terms of number of units or number of parameters is not really the object we should be looking at when asking these kind of questions. And as Peter Bartlett said more than 20 years ago, the size of the weights is more important than the size of the network, which suggests that maybe the question we should be asking instead is, what kind of functions can we represent when we constrain networks in terms of the norm or the size of its weights, and not on how many units or parameters it has. That's exactly the starting point of our work. We consider this complexity measure C, which captures the norm of the weights of a network. Specifically, it's just the sum of the squared weights of the whole system. And the fundamental question we try to answer here, we actually pose and try to answer, is what is the representational cost for some function f under this complexity measure? Here it's denoted by R of f, and by definition it's just the smallest norm, such that we have a network with that much norm, and it actually represents f exactly. Okay, so that's the question. This representational cost we can view in 2 different ways, but quite complementary views. The first one is in terms of inductive bias. So it's fairly common to, when training neural networks, for example, to have L2 regularization on the weights of the network. But what are we actually doing in function space when we have this kind of regularization? So function space is what we actually care about. So this kind of L2 regularization, it's equivalent to having a regularizer in function space that has a penalty on this representational cost R of f. So once we know what this R of f looks like, we know what is the role of the inductive bias in function space when we train a network with L2 regularization. And also in terms of approximation theory, which is how I started to talk, instead of asking the classical question of what kind of functions can we represent by networks where we have a constraint on the number of units or parameters, we should be asking instead what kind of functions we can represent once we constrain the size or the norm of the weights of that network. Our main result consists of a complete and full characterization for the specific case of 2-layer infinite width ReLU networks with single-dimensional inputs. And 2 things to keep in mind here is, first, our complexity measure C of theta does not account for biases, meaning that it captures the setting where we train a network with L2 regularization on the weights only and not on the biases, which is fairly common in machine learning. And second, our complexity measure doesn't account at all for the number of parameters of the network. So effectively, we're considering networks with unbounded number of parameters. So this K in the slides, which is the number of units of the network, it can be unbounded or infinite, whatever you prefer. And to account for that unboundedness on the number of units, what we actually consider is the representational cost, that is the norm, such that we have networks with that much norm, and they can approximate the function arbitrarily well, and we don't really care about what happens with the number of units. It can blow up to infinity, it cannot. What we care about is the actual norm of the network, which can, for example, remain finite and bounded, even as the number of units explodes to infinity. And we show that for functions from R to R, this representational cost R of f is given essentially by just the integral of the absolute second derivative of the function. In other words, it's the second order total variation of the function f. We also have this correction term, which is given by the absolute value of the sum of two derivatives. But essentially, for most typical cases, the first term in the max will dominate this max. So in other words, this shows that the required norm to represent a function with this kind of neural network is essentially just the second order total variation of the function itself. So now that we know what this representational cost is, we can go back to the inductive bias, and we can see that performing L2 regularization on the weights while training a network is equivalent to having this penalty in function space, which accounts for this representational cost. And it's fairly natural conclusion because this second order total variation, it accounts for some kind of smoothness or Lipschitz penalty in this function space. And then we can wonder what kind of functions minimize this, oops, spoiler. What kind of functions minimize this representational cost? And it turns out that when fitting a finite set of points, linear splines are minimizers for the above problem. So we just have a linear interpolation with kinks on the data points. And we actually managed to recover this kind of networks when training, this kind of functions when training networks with just a few number of hidden units. For example, twice as many units as the number of data points. These linear splines are not unique minimizers of the above problem, typically, which includes many smoothed variants, which we typically observe when training networks with more number of hidden units. And to sum it up, we revisited this old and classic question on what kind of functions can be represented by neural networks, but under a very different perspective. And here we're considering a complexity that captures the norm of the weights, the size of the weights of the network, instead of the size of the network itself in terms of number of parameters. This leads to a very natural connection to the inductive bias in function space when we train networks with L2 regularization on the weights. And with our result, we show that there's actually hope for exact characterizations under this setting. And we show that for this specific case, the representational cost has a simple characterization that is essentially the second order total variation of the function. And the proof follows a very straightforward argument. We pretty much take the function, we take the network that has to implement that function, we take the second derivative of each one of them, and just the fact that they should be equal almost fully characterizes what the parameters of the network should be. And from that proof, we draw a pretty interesting connection to Green's functions, popular tools in solving PDEs. Both the full proof and the connection to Green's functions are available in full in our poster, 168. And perhaps most importantly, we open doors to many follow-up problems. For example, how can we represent higher dimensional functions with neural networks? What is the required cost, representational cost for these functions? And also, what is the representational power of different neural networks? For example, even univariate neural networks with more than just one hidden layer, or networks where we have a regularization instead of a L2 norm, for example, L1 or L infinity norm on the weights. And also just plain different neural networks, for example, different activation functions or different architectures altogether, convolutional neural networks, recurrent neural networks, and so on. And that's it. No, this is
only one directional because it counts the number of units effect the representation power.
so this is not really an upper bound. This is an exact characterization.
Yeah, but in reality, you think
Right. In reality, when you have some constraint on the number of units, what you can say, for example, is if your the function you're trying to fit is piecewise linear with 1,000 pieces, then with that representational cost, you can fit it with a neural network of 1,000 hidden units, for example. But in general, for smooth functions, you can't really implement them in reality because it would require infinite many hidden details.
Okay, one more question. Yep. So a common technique that people also use in neural nets is to do something like a layer norm, which is basically after you do your convolution, you add random normalization on your weight. So in terms of your formulation, it becomes like a minimization with a constraint. Have you tried to use your technique to describe that? Because layer norm also have a good regularization.
So I'm not sure if we can relate directly layer norm well to regularization because it changes the optimization quite a bit. For example, if we scale up or down the weights of each layer, it shouldn't actually affect the output of the network. So I think it changes the setting quite a bit. I'm not sure if we can